Bottles knocking models. I wanna bump a beat that goes hard.
Good evening, everybody. My name is Obi-Wan Pez, and this is N Simplex Pachinko, and we are doing some math tonight. So, if anybody has any questions, feel free to drop them in chat or question mark. No? Oh. Well, that's too bad. We do not have access to EnigmaBot at the moment. Oh, hey, Superbrain, how's it going? Been a while. How you been? So, hang on. This thing is all crooked again. There we go. The mat on the floor does not have all the little pokey things that go into the floor and hold it still, so it keeps sliding on me. It's hot. Hey, all right. Working for private industry or that. Well, speak of him and he shall appear. Hey Zach, how's it going? Yeah, so private industry, public sector, or independent education. Obviously keep it, you know, vague or whatever. We don't have to make it too specific. Alright, so last night we were working on polynomials, and we said that if we have a polynomial that has a particular zero, then... Well, this one was asking, given a zero of the function, what could have been one of the what could have been one of the polynomials that had it as a solution. So with this, we had root 3 minus root 2. In order to have rational numbers as our in order to have rational numbers as our coefficients, we would have to have the conjugate of this as well as one of the other zeros. So if we just multiply out, essentially, x minus this and x minus root 3 plus root 2, contracting, nice. Yep, I got a lot of friends who are contractors for the U.S. government, but you know they're technically in private industry. It's just that they do, you know, eventually the accountability goes to the government somewhere. And as such, there's a lot of rules. Right, so we looked through here. That would be another way to at least check some of the possibilities. If we had x minus root 3 minus root 2 times x minus parentheses root 3 plus root 2. Again, this is not like a good way to do it if you're timed. So you're trying to do stuff on the GRE exam. You don't, generally speaking, want to go this route, but you know, this is just another thing that we could do. So in here, this is going to get us x squared. Then we're going to get a minus x times the quantity, right? And then this is going to have a root 3 minus root 2. And plus root 3 plus root 2. Maybe not. Hang on. Let's think about this, right? If you have an irrational number, you have to have its conjugate as a... Hey Rex, how's it going? Glad to see you in. Somewhat. So, like, the best way to do something, really, is to sit down with a person and have an extensive oral examination. I did that. It was difficult. This would be the product. Okay. Okay. Clever. 3, and then that's going to be a minus 2 there. So we get x squared minus 2 root 3 times x plus 1. And then, in order to ensure that we end up with rational values again, right? Because if we just do this and its conjugate, then we still end up with irrational values. So now I think we need another conjugate here, where the plus 1 is just going to be a part of like the x squared term, essentially. So in here we reverse only the root term. I think that actually does it. So this is going to be x to the 4th. Then we're going to get x squared times 2 root 3x and x squared times negative 2 root 3x, so those go away. And then we get, we're going to get 2x squared. Right. And then the negative 2 root 3x and the positive 2 root 3x are each multiplying our x squareds and 1s, which are the same on either side, and then the negative sign is just going to delete all of those as we go across. Moving toward the sound source is different from sound source moving toward you. Yeah, that's, although, did you account for relativity? Ew. How much is it, I guess? How much is it different? Oh, is it because you're also changing angle? No. No, you're probably just doing it face on. One-dimensionally, it would make this much easier. Okay, so in addition, right, our middle terms, as long as they're multiplying something else, end up exactly the same but with opposite signs, so they all go to 0. Then when you multiply them together, that's going to be the different thing here. This is going to be a negative 12x squared. So how we get that is we're multiplying our 2 root 3 on either bit. One's positive, one's negative, so the result is negative. 2 times 2 is 4. Root 3 times root 3 is 3, and then that makes 4 times 3, which is 12. Negative 12. And x times x gets you x squared. Oh. Yeah, that might do it. Or something very similar to it. And then we get, again, our 1s. Well, just going to multiply 1s together. Yeah. So x to the 4th minus 10x squared plus 1. That should, in theory... Yep. Cool. That is the thing we got. I just wanted to double check this the other way, right? So logically, how could we go through it to then... Right. Logically, could we go through it in order to show that it was impossible to get the answer on A, on a quadratic at all, and B, what would the answer be from like a logically consistent way through? So yeah, in order to do that, we end up getting our x to the 4th minus 10x squared plus 1. We had to multiply by the conjugate of the thing with the square root twice. Once at the beginning, but the problem is that it has 2 square roots. It's a little bit like this other problem we did that was, I think it was number 1 actually. Ugh. Yep. A little bit like this, when we went and squared both sides, one of the terms still had a square root in it. And that would have been the same whether we did it just from the beginning and it was the sum of square roots and we square it, right? We take the stuff out of the square roots, but then we've got a middle term that has a product of a square root. Or we move one of them to the other side, and then we have a square root. We square it, it goes away. And then the other side, we have a thing without and a thing with a square root. And the thing without is just without. But the thing with the square root, we square it, the square root goes away. I hate it when that song does that. And then the square root multiplied by the not square root term ends up with a square root at the end here, just like we had in this term. Right, so I think the same thing is at play here, with the solution being the sum of two terms with a square root, where if we multiply by the conjugate, then we're multiplying by our square roots of 2, and like that bit goes away. But then when we get to the first term in both of these, we're getting the sum of the two zeros, which still leaves a square root behind. So then we have to do it again to get the second conjugate to knock out the second term. Goodness. Okay. So actually, let's reset the canvas. And we go with number 13 to start. Yeah, prime factorization of very large numbers is a bad question on a general test, but at the same time, like, doing the other thing that they did for I deleted it. The other thing that they did for number 1 was not, you know, list the roots of this particular question. The question was, find the sum of the roots of this particular equation. So when you do that, that is an NP-complete problem, because now, like, you can't just guess at it. You can't just say, is it this is not, let's plug these into the function and then get an equation. Right. Some of the other ones did have, you know, here are a bunch of either solutions or intervals of solutions. And so, like, if you know what you're doing, yeah, you could essentially build a number line and then say, like, here are the points that they've highlighted as important. Let's just plug in a bunch of numbers between them and see which one is correct. And interestingly, only one of them was adjoining, where it skips only a single number, the number 1, whereas the rest of the options here were all separated by, like, an entire interval. So if you didn't know what you were doing on that one, or if you had to go absolutely had to go the long way and do what I did, which is, you know, plug it into a calculator or actually solve it, then it could take you a while. But I'm a fan of giving the student enough time to actually do it the correct way, the mathematically rigorous way, as long as it actually, as long as they need in order to do it the proper rigorous way. Because I don't really want people necessarily to have to take the shortcuts, have to do some sort of test trick in order to get the correct answer within the correct amount of time. I think that's kind of cheap. But then again, that also means that you're going to have to ask the right questions, which is difficult. Why not just check everything? I mean, obviously, it's the best way to do it. All right, so 13. When the polynomial p of x is divided by x minus 1, it leaves a remainder of 1. Oh no, it's like a Chinese algorithm. When divided by x plus 1, it leaves a remainder of negative 1. Find the remainder when p of x is divided by x squared minus 1. Okay, so I think this is kind of interesting. It's going to be super quick, but it is kind of interesting. If you know, right, p of x divided by x minus 1 is going to be equivalent to 1 mod x minus 1, and p of x over x minus 1, x plus 1, is equivalent to negative 1 mod x plus 1, then what that means is that p of x is going to be equivalent to no, I don't need to do that. Hang on. Right, okay. This also means that p at 1 is equal to 1, and p at negative 1 is going to be equivalent to negative 1. Right, the remainder theorem says that the remainders of our division are going to be equivalent to the function values at those points. And in this case, again, what we've got is that x is equal to 1 and x is equal to negative 1 for each of those. Hey Viv, how's it going? Yeah, pretty decent. Yorkshire has been good for today and yesterday, so it actually wasn't too bad. Yeah, no worries. So, yeah, my typical name here is Obi-Wan Pez, or just Obi for short. It's one of those things if you're... is me. Yeah, anyway. I could, that might actually be a problem. I don't know exactly. Like, the opening itself is square. Granted, right? Tic-tacs, in theory, could fit. I don't know if it would jam, which would be a bad thing. Or if they're too deep, that would also be a problem. I have to get the technical specifications on Pez before I attempt anything. Well, Superbrain, I think I don't entirely know what you're talking about, and maybe that's a good thing. Was that the riots against joining the EU, or was that opposed to the closing of the coal mines, or worse? Okay, so let's look at it this way. If P of x over x minus 1 is going to imply that P of 1 is equal to also 1, then let this be Q of x, and then we want Q of x over x plus 1. Now, we don't know what this is going to be, technically. But we could also do this as P of x over x plus 1, which is going to imply that P of negative 1 is equal to negative 1. If we let this be Q prime, no, don't do prime, Q star at x, then we want to know what Q star at x over x, x minus 1 is going to be. But either way we do this, this should get us the same thing. Right? Because either way, a group around Tom Scott on a road trip like 10 years ago. Interesting. Probably gonna have to look that up. Right, both of these things should be the same. That q star at 1 should be the same as q at negative 1. So how do we justify it? How do we make that work? So this is like n times x minus 1 plus 1. This is like m times x plus 1 minus 1. I want to say it's the product of both of them, which is just going to get us negative 1. But I'd like a little more proof. So we're just associating, essentially, which one we're doing first. Are we taking the... remainder of the division of x plus 1 or x minus 1 first, and then we want to know what happens when we divide by both. Alright, so let's do one just for fun here, like x to the third plus 7x squared minus 4x minus 10. So not particularly anything factorable or nice. This is somewhat randomly created, so it's quite possibly really nasty. And then we'll use the two that are here. So we're going to divide by x minus 1. And this is going to get us, we have a 1 at the outset here. So that's a 1, multiply up is 1, add down is 8, multiply up is 8, add down is 4, multiply up is 4, add down is negative 6. Alright, and then we also divide by x plus 1. That's also an interesting question. What counts as the remainder in this next one? Because this is going to be constant, and this is going to be a remainder of x minus 1. That's x, and this is x squared. If we divide by another x, x plus 1 in this case, we end up with 1, negative 1, 7, negative 7, negative 3, 3, negative 3. Now this is the remainder of both. This is the remainder of only x plus 1. That's a constant, and that's an x. Secondary question, right? If we have 1, 7, negative 4, negative 10, and we go the opposite way, so we do negative 1 first, we're going to end up with 1, negative 1, 6, negative 6, negative... That definitely should not happen. No. No, 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 no. That could not possibly be the case. Hang on. All right, x cubed, 7x squared, negative 4x, negative 10. And this is where the memory fails. 7, negative 4, negative 10. Wow, okay. Fascinating. Happen to pick like the one time. Okay. So that also leads us in this particular case to say that this is x plus 7 minus 3 parentheses 1 over x plus 1 plus 1 over x squared minus 1. Both parts. It's wild. But that's messed up. Because they'll combine. Right. They will combine in a specific way. So minus 3. This is going to end up being x minus 1 plus 1. There we go. Times x squared minus 1. This is x plus 7 minus 3x over x squared minus 1. So in theory, right, our remainder should be negative 3x. Well, okay, this is one that I made up, so this is not the question that I actually want to answer over there, but nonetheless. All right, and then 1, it's going to make this 1, 1, 7, 7, negative 3. So this is x plus 7 minus 3 over x plus 1? No, minus 1. That's not right. Okay. So if we say we want now x plus 1 times our 3 all over x squared minus 1. It's going to get us negative 3x minus 3 over x squared minus 1. Now this is distinct and different from the other one. Well, I was trying to see how the relationship holds when we do division of polynomials in two different orders. And unfortunately, it doesn't. At least at the moment, right? I screwed something up somewhere. There must be something wrong here. Be damned if I can find it, but, you know. It is long division of polynomials, yeah. Ruffini. Not exactly sure myself. Yeah. Yeah. Special case of synthetic division in which the divisor is a linear factor. Yeah. I should probably know that. Paolo Ruffini, 1809. Gonna have to put that in my notes somewhere. Give him proper credit. Hang on. Don't do that. There we go. Yeah, ruffian. Yeah. Close. So, right, I made up a polynomial. I said, let's do x cubed plus 7x squared minus 4x minus 10. Completely made up. And then I said, let's do both x minus 1 and x plus 1, because those are zeros that we were using for the previous one. So I went through and I said, now, if we do x minus 1 first, that's going to be an x equals 1 as our 0. So then when we do the division, we have a 0 here. The 1 comes down, just makes 1. We multiply by the 1, which becomes 1. Then we add, going straight down, 7 plus 1 is 8. We multiply by 1. So again, just write the number. It's 8 plus negative 4 is going to be a positive 4. Right? Times 1 is going to get us 4. Minus 10 is going to get us negative 6. Now, this has, because we started with x cubed, it's getting knocked down to an x squared, plus 8x plus 4, which is the constant, minus 6 over x minus 1, because that's what we already divided by. All right, then we take x plus 1, and we say if x is equal to negative 1, then we do the same division algorithm. We said that this is going to be a 1. Multiply by negative 1 gets us negative 1. Add to 8 gets us 7. Multiply by negative 1 gets us negative 7. Ah, there we go. Yes, it is. Oh, wait, no, hang on. This 4 is positive because, right, we had the negative 4 up here plus 8 got us positive 4. Okay. So add those. 4 plus negative 7 is negative 3. This now has a remainder of x plus 1. We multiply by negative 1 to get 3 up here. Add negative 6 plus 3 is going to be negative 3. This remainder is for both terms, an x plus 1 and an x minus 1. Then, when we write this out in long form, this is going to be 1x plus 7 minus 3 over x plus 1 minus 3 over both terms. So x plus 1 and x minus 1 multiplied together gets us x squared minus 1. Since I don't really like this form in the moment, I said let's pull out the negative 3 and then try to combine these two terms. So we said the 1 over x plus 1 can have an x minus 1 multiplied top and bottom, which gets us x minus 1 over x squared minus 1. And then the right-hand one is going to be 1 over x squared minus 1, so we just have the 1 here. The minus 1 and plus 1 becomes 0, and we're just left with x over x squared minus 1. Times the negative 3 on the outside becomes negative 3x over x squared minus 1, plus our x plus 7 out the front. Yeah, so turns out... No, sorry. 1 is not a 0. I had just picked some because I was just like, I just want to use the same numbers that we used over there. And I did it blindly. As it turns out, oops, it does in fact have a 0 at x equals negative 1. which is the x plus 1 term that we were dividing by. But I found it rather interesting because, again, what we had here shouldn't be dependent on order. Wait. Is that x minus 1? Oh. No. It's whatever we just divided by, so that's x plus 1. The order in which we divide should not matter, right? If we divide by x minus 1 and then divide by x plus 1, we should get the same thing as dividing by x plus 1 and then dividing by x minus 1. Right. Should not matter. So then we move over here and we say, okay, let's do x plus 1 first, so we get negative 1 up here. And then we drop the 1, multiply by negative 1 is negative 1. Add down is going to be 6. Multiply up is going to get us a negative 6. Add down is going to get us a negative 10. Multiply up is 10. Add down is 0. Because we have a 0 remainder. Wait. Yeah. Okay. We have a 0 remainder for x plus 1. Okay, this is constant, this is x, and this is x squared off of the x cubed that we had here all the way down to constant that we had here. Which means that this is x, this is constant, and this is remainder of x minus 1. And then this is going to be a 0 remainder for both. Right? Nothing changed here. Oh, it isn't though. Fascinating. Because here we would get a negative 3, which added down would get us a negative 3. Okay. That is the weirdest thing I think I have ever... Okay, they agree now. I hate it, but they agree. Okay, and since that would give us a plus 3 here if we factor out the negative to the front. Right, so this is going to be a negative 3x over x squared minus 1. X plus 7 is term out front. Okay. So the remainder of both terms is going to be a negative 3x. The remainder of each of them individually was a negative 6 and a 0. That in no way helps us really get negative 3x as our remainder for the combined. I was hoping, but what I wanted to have happen was that this was going to be like the product of the two others. Which may or may not be true, but that doesn't guarantee it. I think it might end up with something like this. Gonna have to be a little more careful. Okay. So if we do something weird, which, like, good. Let's do something weird. P of x is going to be equivalent to, which really we could just write it as, some type of n times x minus 1. Right, some number of n's times x minus 1 plus 1. And also, p of x can be written as m times a number of x plus 1's minus 1. Right? Because if we get p of negative 1, this is going to be 0 minus 1. So we end up with negative 1. If we end up with p of 1 in that version, this is going to get us a 0 plus 1, so we get 1. Alright, so this agrees with our original premise. Then we want to know what's going to happen when we take both. So p of x over x squared minus 1 is going to be equal to, k times some number of x plus 1's and x minus 1's together plus a remainder. What is the remainder? We divide by both terms. Ah, no. P of x is equal to that. So either p of x, p at 1 or p at negative 1 are both going to get us 0 plus r, so it's going to be whatever remainder this is. It doesn't really matter which one we plug in. P at 1 and p at negative 1 are going to get us equivalent values. Right? R. Which at the very least does confirm that we're going to have one remainder when we divide by both of those terms together at the same time. Right, so from Not either. Both. Well, clearly that's not correct, right? P of 1 and P of -1 are opposite signs, so that doesn't work. But what is it really asking me for? Doesn't have to be a constant. We can have... We're allowed to have... other terms. So R can then break into, right? This is going to be like A over x plus 1 plus B over x minus 1 plus C over both. Alright, and technically all of this is called the remainder. Okay, let's go like this. P at -1 is going to equal 0 plus. I can't do that because of the A, or because of the A term, and the C term for that matter, right? Those become undefined. Okay. Cool. Wait. That is when... Okay. Not entirely. It's only partially true. So, P itself, right, could be broken down into these parts. But this was not 1 over x minus 1, and this was not -1 over x plus 1. These denominators don't exist yet. Rather, what we do have is, right, P of x over x plus 1, x minus 1 is going to be equal to, okay, there is some number of wholes, x. Sorry, no. I literally wrote k. Some number of whole numbers, k, that are evenly divisible. Then we have the bits a, which can be remainders of x plus 1 only, We have b, which are remainders of x minus 1 only, and we have c, which are remainders of both. Okay, then when we multiply it all the way through by those two terms, x squared minus 1 or x plus 1, x minus 1, then we get k times both. This is the part we don't care about, right? We will plug in each of them 1 and negative 1, and that term will just go away. Then we get a times the term we didn't have, x minus 1, plus b times the term we didn't have, x plus 1, and then plus c, the like true remainder that didn't exist here. I think I'm rambling. Sorry. Ads are going to start in like 5 seconds. That's why I was trying to hurry this up. I'm going to stick around here, but we'll get right back to this. Thanks so much, everybody, for sticking around, and we'll be right back. Okay. So we know that b and c need to be constants. However, we have this relationship that's going to exist where, right, we've only got two equations and 3 unknowns. So it creates a little bit of a problem, but we can trade off between A and B because they both have x's in them. So like if we set one of them to a specific value, then that'll force the other one to be another different specific value. But again, should allow us to just trade amounts between them. We need a certain number of x's in total. And in theory, that should either be 1 or 2 or 0. Or -1, I suppose. Given the answers that were in the book, or the possible answers. Right, so A, B, C, D, and E. -1, 0, x, -x, and 2x. On balance, judging by ridiculous standardized test rules, the answer probably is either x or -x. But don't do that to yourself. Okay. That's not necessarily true. You won't necessarily get A equals B. You can get a specific number, though. So let A equal I don't know. Let A equal 2. Okay, experimentation. That'll mean that -1 is equal to -2 times 2 plus C. Therefore, this is -4. Add 4 to both sides. C is equal to 3. Which will mean that 1 is equal to 2b plus 3. Subtract 3 from both sides. Oh, we're going to get something nasty. Oh, no, we're not. Never mind. -2 divided by 2 means that b is equal to -1. So we're going to get, if we do this the way that I just said, this is going to be 2x minus 1 plus, nope, minus 1, yeah, or plus -1 times x plus 1 plus 3. And then if we just combine all this stuff together, it is the remainder, right? This is going to get us 2x minus 2 minus x minus 1 plus 3. So then this is going to be x, and then this is going to be -3, and that's plus 3, so that's going to be 0. What'd I say? Now, I think it would be worthwhile to at least say, okay, what if we picked a different one? So let A equal, 5. negative 5. Why not? Right, if a is negative 5, then negative 1 is equal to negative 2 times negative 5 plus c. This is going to be 10. We need to subtract it from both sides. And then c is equal to negative 11, which then leads to 1 equals twice, nope, that's b. Twice b minus 11. Add 11 to both sides. This is going to be 12 equals 2b, so therefore b equals 6. And then when we combine this, right, we're going to get 5 x minus 1 minus 11. Nope. Come on. Plus 6. X plus 1. That was a negative 5, wasn't it? Yeah. A is negative 5. I wrote it myself, you know, you'd think. Is equal to, nope, plus a negative 11. Okay, so negative 5x plus 5 plus 6x plus 6 plus, well, minus 11. This is going to be positive 11 minus 11 is going to be 0. And then we have a negative 5x plus 6x, which is also going to get us an x. Okay, so the actual answer here is just positive x. So, option C. I think this is actually like the shortest algebraic method to get this. Yeah, because if you do both, you're going to get these, which then allows you to say, here your p of 1 and p of negative 1 get you these values with knocking out a bunch of zeros, and then you get a system of equations. Yeah. So, that requires a little bit of insight. It did not work so well to do all this other stuff out here that we were trying to do. I mean, that was literally a different problem and not one that we were trying to do. But all right, 14. Given that p of x is a real polynomial of degree less than or equal to 4, such that we may find 5 distinct solutions to the equation p of x is equal to 5 what is the value of p of 5? My goodness. So that's not possible. We do get A, B, C, D, E. 0, 1, 4, 5. And cannot be determined. Cannot be determined from the given information. This one's going to be E, right? By fundamental theorem of algebra. Specifically, right? If P of X is equal to 5, then P of X minus 5 is equal to 0 is really what we're looking for, right? What are the zeros of this particular function P of X? It's been shifted down 5. Well, from the fundamental theorem of algebra, we know that the number of complex zeros of an nth degree polynomial is exactly n. So if the degree is less than or equal to 4, there are only a maximum of 4 zeros, roots, solutions, whatever you want to call them. Right, there's no way to find a fifth. This says that we have 5 distinct solutions to the equation P of X is equal to 5. That's not possible given that our degree is only 4, at a maximum of 4. So, cannot be determined from the information given. By the fundamental theorem of algebra, again, we know that the number of complex zeros for an nth degree polynomial has to be exactly n. Can be no deviation. And that being said, right, well, wait, why does a cubic polynomial sometimes only have 1 0? Right, in that particular case, it has 1 real 0 and 2 complex zeros. So, those are away from the x-axis. So it'll go through the x-axis somewhere, and then it'll have another bump, or it'll like slow down a bit, but keep going. There's a number of different shapes it could have. But the point is that it will not go back on itself and touch the axis again. And yeah, our P of X, if it has degree less than or equal to 4, can only have at maximum 4 possible solutions to any equation which has a degree 4 polynomial. Here we see P of X is equal to 5, therefore we can move this over and make it P of X minus 5 equals 0. Again, that just shifts the function down 5. It doesn't change the nature of the function itself. So it doesn't add any more zeros than the degree allows us to have. It could potentially add or subtract real zeros from another shifted version of itself, just depending on how many times it'll go through the x-axis. But that's going to be that issue. All right, 15. Walking Stick Library, good evening and welcome. This is the subject test to the math test, yeah. So this includes, the book for this includes all stuff from pre-calculus all the way through complex analysis, complex variables. So, yep, it's a lot. We're gonna skip this one here. All right. If the roots of the equation x squared plus bx plus 1 equals 0 are the squares of those of x squared plus lowercase bx plus 1 equals 0, where big B and little b are distinct from each other. Right, it's the only way that can actually happen. Express big B in terms of little b, and then we have our 5 options that they give us. 2 minus b squared, 1 minus b squared, b squared minus 1, b squared, and b squared minus 2. Now see, this one, right? This is pretty nasty, but a good question in terms of, like, I'm not going to be able to look at this and know just right off the bat which one of these is going to probably be the answer. Unlike some of the previous questions where it was like, you know, I can narrow it down to 2. Right? This one, not this one. This one was a little ridiculous because it was like, you know, what's the remainder of some stuff? If you don't know what you're doing, it could just as well be any of them. But at the same time, like, there's only 2 of these that have one term. You could probably eliminate 0 because it's like, you know, neither of these 2 things. The original polynomial is not divisible by either of these 2 things. So why would its product be able to divide evenly, right? That just doesn't happen. You're going to have a remainder. So it's not 0. Initially, I'd thought maybe it would be like the product of these 2 zeros, or the quotient of these. Nah, probably not quotient. Probably it might be the product of these other 2 remainders. So that could be 1. That seemed like a reasonable answer. And then 2x was like, you know, could just as well be that. But x and minus x at the same time, it just like set off a little alarm bell that was like, you know what, I think the answer is going to be one of those 2. Turned out I was right. It's a terrible way to run the exam like through your head, but this one was nice. It's just like specific knowledge about polynomials, right? Fundamental theorem of algebra tells us that the number of complex zeros of an nth degree polynomial is exactly n. So if we have a degree 4 polynomial, you can't have 5 distinct solutions to any equation that involves the same degree, right? 4 or fewer. It's just not going to work. Okay, so if the roots of the equation given here so this is easily done with this is easily done with completing the square. So this would be x plus something squared. This is also x plus something squared. In both cases, no, not necessarily. Okay, because if it's like 5 or something, then that's not going to work. Yeah, don't mind me. It's fine. We can, in fact, complete the square, but that does we don't know exactly what it's going to be. So it might be slightly ugly. You never know. Right, and they could be negative. So, right, anyway. Essentially, we're looking at the quadratic formula for each of these, potentially. Negative big B plus or minus square root of big B squared minus 4. A, C are both 1, so it's just B squared minus 4 all over 2A is 1. And then here, this is the exact same thing, but now it's lowercase b and what was it? The roots of the equation with big B, so the ones up there, are the squares of are the squares of these. Oops. All right, copy, paste. Cool. Yeah, I guess we could have also done it in terms of completing the square, but then right, we'd have to. I feel like it would no, because then you still got 2 terms, right? You still got 2 terms. Yep. So this is from 2002, or at least that's the copyright. I think you and I may have actually discussed this in a previous one. You said that your version is also the 2002 version. I ended up taking my GRE in 0405. So if you had done it in 09, makes sense that it's probably even the same version. Okay. Probably. Right, and their product is going to be 1 in either case. Oh, I guess. Right, so then this is going to say that. That is also slightly awkward, isn't it? It never said that the... It did never say that the zeros had to be real, but it is slightly annoying still to just be like, oh no, the sum of the squares of these two numbers is going to be negative. Oh, no. It doesn't even have to be negative, right? It could be a negative number. Quite possibly. Let's go through and make sure it works, right? Excuse me. Right. Right, because P plus Q is going to be little negative B. So P squared plus 2PQ plus Q squared is going to be equal to little b squared, P squared plus Q squared, yeah. B squared minus 2PQ. Right, and we also know that PQ was equal to 1. Right. Finally got an A. Right, 2 minus b squared. 2, yeah. 2 minus b squared. Yup. Awesome. All right, 16. No, I just do Twitch. Working on deciding if I want to do anything else. Currently, I have 2 treasurer positions with volunteer organizations, so like that's probably going to keep me busy enough that I don't like need to work, but not to mention, you know, in addition, if I were to actually go to a school and say I would like to teach here, they're probably going to make me jump through a bunch of hoops to get actually certified. And, like, I've never really actually become certified. When I got close to getting my... What was it? When I moved to Maryland from New Hampshire, they told me that I would need to, you know, set up my account on the Department of Education website and all that cool stuff. Sure. So I went in and I did that, and then when I got pretty much everything done, they were like, okay, so you need 4 classes that were not on your transcript that, you know, we have as a requirement here in Maryland. Reading in the content area 1 and 2. Human exceptionality. So basically, how do you teach honors students? How do you teach students who need more help, like significantly more help? And online assessment or something like, or no, I did it online. It was a class all about assessment. And when I took all 4 of those, I submitted everything and I was like, all right, I'm good, right? And they're like, yeah, no, your references have run out because it's been 2 years. And I was like, screw this. And I joined the same college where I took all those courses. I joined their math department. And it was in addition to like the department chair that I'd had in the public schools that I was intending on, you know, working for them in perpetuity, ended up not really liking my particular style, and I grant you, I was inexperienced, so it was effectively like my student teaching year, essentially, but I'm getting paid $40,000 a year, so, you know, you better do better. I wasn't super great at it, but, you know, things were going okay, and then she just did not like my teaching style and tried to get me to do a bunch of stuff that like I was never going to be able to do in the first place. You know, I want you to plan a bunch of activities that get you to do X, Y, Z, and I'm like, I just can't. Like I can't do this presentation up here in, you know, a completely different personality than I have. And so at the end of the year, she was just like, yeah, well, I don't think we want you back. And I'm like, all right. Don't really want to teach here anyway. Got mistaken for a student too much when I was, you know, clean shaven. And the last day when I was wearing a polo shirt and jeans, some student who was trying to start fights in the hallway, I don't think he mistook me for a another student, but he definitely was about to throw a punch at me, and I was like, yeah, no. Like, I'm not playing that game. All right, find the largest value of b such that 1 plus bi satisfies the equation x cubed minus 3x squared plus 6x minus 4 equals 0. Okay. And b is a real number is guaranteed. So, what is that value of b going to be? We have 4 possible values, 2 of which are going to be positive, and 2 of which are going to be identical but negative. So, no, wait. Oh, nope, that's a third-degree polynomial. Woo! Okay, so given that every root has that particular form, we cannot factor this nicely. So there's a few ways to look at this. We could do this as 1 plus b goes into 1 negative 3. This is going to be gross. 1 plus b I. Do it in general. Let's see what happens. Alright, 1 plus bi. No, sorry, that's 1 plus, that's just 1. 1 plus bi is going to be here. Negative 2 plus bi. It's going to get pretty nasty, but it'll do something all right. Okay, this is going to be negative 2 minus 2bi plus 1bi minus b squared. Negative b squared minus 2. That is a plus 1 and a minus 2, so minus bi. Add 6. It's a negative b squared plus 4 minus bi. Alright, multiply those together. The real part is going to be negative b squared plus 4. And then multiply the 2 bits together there is going to be a negative b squared I squared, so that's going to be plus b squared. That actually cleans it out pretty nicely. So we just end up with a 4. Ooh, nice. We should expect that. Nice. Because here the real parts should go away, and then we just get the b's left over as part of the complex, or the non-real. That's pretty nice. Alright, this is going to be it. Do we literally just get another cubic polynomial? This doesn't surprise me. Or at least I should not be surprised. Alright, so that's the real stuff. Imaginary, we're going to get a negative bi and a plus negative b squared plus 4 bi. So yeah, that ends up going away. We just get a 4 left over. Then over here with the i's, alright, plus we get a negative b squared cubed, negative b cubed, right, multiplied by the other one that's in there, plus 4b minus b. So actually that's not too bad, all things considered. So 4 plus parentheses negative b cubed plus 3b I. Negative 4 plus parentheses negative b cubed plus 3b I must equal 0. Right? 0 plus 0i. So therefore, it is another cubic polynomial, but this actually transformed it into a much nicer form. Because now we got to solve for that cubic polynomial. So negative b cubed plus 3b is equal to 0 means that, right, option 1, b equals 0. Option 2, b does not equal 0, which means that we can divide by b. And so that's going to be b cubed is equal to 3b, or b squared is equal to 3. So then now we have two solutions who are equidistant there. This is the absolute value of b is equal to root 3, and therefore b is equal to plus or minus root 3, or 0, as our three possible solutions. The largest one is the square root of 3. Just breaking my rules all over the place here. There we go. All right, so this would have had us have the following: a is 1, b is root 2, c is root 3, d is 2, and e is 3. All right, just put them in numerical order. C was root 3. $17. If a and x are positive, big A is equal to little a squared. Express the following in simplest terms. Of x. Right, a raised to the log base a of x plus log base capital A of x. It's inconvenient, but all right. In order to get these things together, we need to have the same log base. So a is going to be equal to, no, a raised to the log base a of x plus, this is the log base little a of x over log little a of big A. The good news is that we have a relationship between those. Log little a of x plus, this is log little a of x over log little a of little a squared, which is just going to be 2. So again, logarithms are a question. What exponent on this little base that we have down here is going to get us this thing inside the log. So in this particular case, what exponent on a is going to get us a squared? It's literally right there. It's 2. All right, so a log little a to the log little a of x plus 1/2, right, the 2's in the denominator, log base little a of x. Those are the same thing. So now we're going to get 3/2, a raised to the 3/2 log base little a of x. That's now an exponent. So a raised to the log base little a of x to the 3/2. Exponential functions and logarithmic functions of the same base are opposite, are functional inverses of each other. So here, a raised to the log base little a is just going to go away, and we just get x to the 3/2. Okay, 17. All right, what were the actual options? All right, 2x, x squared, square root of x, or that would have been x to the 1/2, x to the 3rd, and x root x, which is x to the 3/2. Alright, so our solution here is E. X to the 3/2 was what we got when we just did this out algebraically. Works out pretty nicely. Alright. No, not 20. I wish. 18. Just a reminder, if anybody does have any other questions that they would like answered, feel free to message in the chat window, or we can go to Penn Center's Discord. Penn Penn Center's Discord. What's going on there? Right here. All right, this is Penn Center's Discord. He has been doing Legend of Zelda Ocarina of Time, as well as many other Zeldas. However, Ocarina of Time seems to be a decent speedrun category for him, and also been doing randomizers. I think maybe even an archipelago randomizer, where you like get stuff for your other partner in addition to yourself. It's wild. And other shout outs that we have here. Walking Stick Library was just in a little while ago. They've been working on educational type stuff. Typically, I've been in there, and I gotta tell you, I have not been paying attention because it is not in my proper time zone. Sorry. But definitely, go check them out. And we have... Zach, either the 2i Pi, was in earlier and typically does a lot of mathy type stuff. Also, we've been known to play games all together. We have, as a small community, all of us mathy type people have been doing. Yeah, I figured you were either lurking or had gone off to go lurk. So yeah, we have been known to play games as a small community as well as individually. And Zach, if you have any projects that you've been working on that you would like to shout out, feel free to. Did we finish Good Job ever? Well, we did not finish Good Job. No, I did not either. I've been waiting for another time when we're all getting together for it, but I didn't want to spoil myself too much. But, I mean, at this point, right, there's a good chance that I should just stream it. It's been a year, yes. It has most definitely been a year. Ads are going to start in about 2 minutes, so we're going to discuss anything else we got here. Funniest talk ever. I don't know, that's a pretty bold claim. Scuola Internazionale Superiore di Studi Avanzati. Italian? Ooh, that sounds like a good one. Sorry. Just found out that somebody from YouTube is streaming on YouTube. One follower away from approximately 200 pi. Yeah, I know. Okay. I'm going to take a little walk here while ads are playing, get 3 minutes, and we'll see you back here in just a little bit. Thanks for coming, everybody, and yeah, we'll be right back. My name's Obi-Wan Pez, just in case you're new here, and this is N-Simplex Pachinko. Welcome. Howdy Pie. Good evening and welcome. And how's everybody doing? Still working on the chapter 1. No, actually, it's not too bad here. Yorkshire dropped to 70 degrees yesterday, and it's been hovering around 65 to 75. No, not even that high. Like 65 to 72 today and yesterday. So it's been nice. We've been this room gets a little warm just because I have 2 computers running here, and most of them are doing parallel processing stuff. Not parallel. Technically it is, but whatever. They're doing shared processing projects for Boink. So, yay science. So they get kind of warm. This room usually gets up to about 70, 75. Sometimes when it's like warm outside, it can get up to 80. When it was 87 outside, it was very warm in here. But we got the air moving, and it kind of kept it more or less. It felt like it was probably 80 to 85, which is still pretty miserable. But I ended up... We are reading in our book club. Let's get rid of that because that's an official document. Don't really want you all to see it, no offense. Salvation by Peter F. Hamilton. It's a... If this is true, and all of these are part of the same series, it is one of 5. 90 in Georgia, yeah. So, this does get a little wondery, but I like it so far. The like the main story that they start with, come to think of it, can't 100% remind myself what it is. Right, so there's like an prologue bit at the beginning, and then it goes to this group of people who's in 2204, and they're talking about there's this creation of portal technology, and so it's really cool. The company is well established throughout the entire world, and it's about like what's going on in 2204, so like now. I consider that the present of the story, even though that's not technically true. There's a group that's in the future from them who are a bunch of students who are just about ready to graduate, and like their world is under attack, so they are the salvation of their particular species. Their particular species is up in space. I think that they might be descended from humans, but I can't be sure. I haven't read far enough yet. And like to their species, they were genetically modified in order to be one of 2 genders. So like their parent species is agendered. They have, or no, they have an interesting dynamic. I think it's the same people. They spend like a 10-year cycle between male and female, and they bounce back and forth. I have no idea how that works, but that is the conceit for that particular species. And in order to survive, they've created this particular generation of students to split into only males and only females. And there's a bunch of dynamics there that they're getting used to because it's not their culture. And then there's also the past. So the people in 2204 are talking about stuff that's happened in their past. Humans in 2204 live over 150 years easily as long as they're wealthy enough. Go figure. And the people in question are like CEO level and higher. So, yeah. So there's a bunch of dynamics of all sorts of cool stuff that's going on, and I don't know how it all plays out yet. I'm only about halfway. Third. And I've been doing a lot of reading lately on this because it was so miserable at night. I would just lay down in the entryway next to our front door, where like there's only concrete around me, essentially. Where it was just, that was the coolest space in the entire house. Just like right next to our entryway. Yep, cool, sounds good. Let the air play over me. Yeah, so like our couch, our living room, our kitchen and living room are attached, and in the afternoon the sun comes in through that side of the house, so like the only way to read really is to either turn on the lights at 4 p.m., which would just be ridiculous, or open up the window, at which case, you know, open the curtains on the window, in which case you've got a huge sunbeam. You know, the sun is a deadly laser, lighting up and heating up a good portion of the living room. So it's just, I was just like, I'm done. I was wearing shorts and it was still uncomfortable. Like, there's something else I wanted to say about either salvation or something adjacent to it. I don't remember. It's fine. I'll remember after stream. Alright, so log of x squared is equal to 2 log of x. Okay, so this is saying that the log of x times the log of x individually is equal to 2 times log of x. So, in this, we can comfortably divide both sides by log of x, because the only objection... Wait. No, we can't. Never mind. So, we have two options. One is that the log of x is equal to 0, because that can happen. Right? It took me a second. Again, the logarithm asks the question, what exponent? So in this case, our base is 10. Our exponent is 0. So 10 raised to the 0 is going to get us x. So x is equal to 1. Right? Or log of x is not equal to 0, in which case we can divide by log of x. Totally got it backward. It's all right. We're good. All right, in which case these eliminate, this eliminates, and we get the log of x is equal to 2. So the exponent on a base of 10, which gets us x, is going to be 2. Or 10 to the 2 is equal to x, which is 100. So the roots for the following equation are either going to be 1 or 100. Oh, of course you did. Of course you did. Hey guys, guess what log they're using? This is not the log base 10. It is, in fact, the log with base e that they're not telling us about. Yeah, natural log. So this is a thing. It doesn't. I mean, at the very beginning, in the section where it talks about logarithms, there's a good chance that it actually does say, hey, by the way, we use natural log as log of whatever, which is also a common thing for like computer science. There we go. Yep. So there's a nice little box section up here, which says in the GRE math test, the e is understood. So log x means log base e of x. And it's important to be aware of this since many pre-calculus and calculus texts and calculators, log x denotes log base 10 of x. And the abbreviation for log base e of x is ln x. So it does say it in the section. But I hadn't actually done anything in. I didn't do that section. Huh. LG. Interesting. That's slightly gross. I would understand like LB for log binary. Why LG? Is it just that they wanted an abbreviation? That one seems arbitrary. Yeah. So like, right, ln, when we write it, this is so right, if it's French, and if it's not, I'm screwing myself over here, but if it's French, it would be like logarithme naturel, right? Like, yeah, so Euler was the one who, like, came up with a bunch of the notation. So, if it was, in fact, Euler, then his primary language was German, but he was Swiss, so, you know, French is just as natural when he was working with it, especially since the primary, like his primary contributors were the brothers Bernoulli. And like his contemporary, one of the other students at the same time was Daniel Bernoulli. And the Bernoullis were French, despite their name, which technically I guess is Italian. It's Switzerland. Everybody's from everywhere. Okay, so anyway, this might be a reason. Read the answers. At least just read them. Make sure that you're understanding the exact same thing. So we got 1 e to the negative second. We've got 1 root e, or e to the 1/2. We've got 1 and e squared, which was our answer. Lingua franca. Right, x is going from 0 exclusive to infinity, and x is going to be a member of all reals. Right, well, x is definitely not a member of all reals due to the fact that, right, this is logs, and there's no, like, there's no stopping it from becoming negative inside the logarithm. So we have to say, okay, the domain is going to limit it to non-negative, or in fact, positive only. Can't have it be 0, can't have it be negative. So 0 to infinity is a decent, like, domain for the logarithm, but this is not the roots of the equation. We figured out that there are, in fact, a discrete number of roots, right? In this case, 2. So c works for us, 1 and e squared. The hyperbolic sine function. Is defined as follows. Sinh of x, oftentimes what people call it, is going to be e to the x minus e to the negative x all over 2. All right, find a formula. Oh, man. For inverse sine of x. Okay. This is the math subject, yep. So this is the pre-calculus section of it, which is all of chapter 1, and we've been working on for a little bit. But this does extend then to Calc 1, Calc 2, vector calculus, linear algebra. Wait, does it do vector? Now that I'm thinking about it. Most of it appears to be part of Calc 2 in this book. Right? Gradient, min-max problems, line integrals, double integrals, and Green's theorem. All listed as part of Calc 2. Interesting. Analytic geometry and partial derivatives of R3. Huh. Okay, so that is what I would call Calc 3. So that's So yeah, vector calculus, multidimensional calculus, is all listed here in Calc 2. Calc 1 includes differentiation, anti-differentiation, polar coordinates, arc length, volumes of solids of revolution, right? That is where I would draw the line at Calc 2. Polar coordinates, arc length, natural, exponential, and logarithmic functions. In order to do integrals of natural log, you need integration by parts. So I think that that's probably what that is. L'Hopital's rule, improper integrals, infinite series, and power series. They list that as Calc 1. Interesting. Good times. Differential equations, linear algebra, number theory, abstract algebra, set theory, combinatorics, probability statistics, point set topology. That's going to be a new one for me. Real analysis, complex analysis. So yeah, that goes through all that stuff. I probably looked at point set topology when I was in, 2004, 2005 when I was taking the GRE, but I never had to take topology. It was an option as one of my electives, and my fiance at the time, now my spouse, was always talking about how awesome it was, and so I was like, kind of feel bad that I didn't take it, but at the same time, I had gen eds to complete and stuff like that, so because I took a few electives that didn't count, but I don't regret it. Okay, find a formula for inverse sine. So when we do this, we're going to get y is equal to e, not x to the e to the x minus e to the negative x all over 2. I'm going to multiply by e to the x, top and bottom. And realistically, I could do it to the other side as well. It's all fine. We'll just do that instead. And then we'll multiply both sides by 2 as well. So we'll get rid of that. The e to the x is going to get rid of the e to the negative x, and then it's going to reinforce e to the x to become e to the 2x. It's going to be inconvenient, but to e to the 2x minus 1. So in theory, right, we can do this as e to the 2x minus 2y e to the x minus 1. And now this ends up becoming quadratic. It's a little gross, but did I take analysis? So I took real and complex analysis as part of grad school. I did not take either of them as undergrad. I took linear algebra, the senior level linear algebra, which I think was required. I can't remember if it was like strictly required or if I took that because A, my spouse was in that class, B, it was her favorite professor in the entire world, and so I figured like she would be able to interpret his notes for me. Because some of the things he did were wild. This was 2005. He got his PhD, quote, in the 40s. He was like mostly balding with a salt and pepper ponytail that went pretty much all the way down his back. And he would sit in his chair and lean back a bit and talk like this. Usually put his feet up. Yes, his eyes were closed most of the time, but like he was constantly asking questions and trying to probe our minds and things like that. So, I mean, he wasn't sleeping or anything. It was just... I don't remember exactly when it was that I found out that he passed, but like I said, he was my spouse's favorite. So I was like, I'm really sorry. She was like, I mean... Again, he got his PhD in, quote, the 40s. Okay, so e to the x is going to be equal to, this is negative b, so 2y, plus or minus square root. Negative 2y parentheses squared minus 4, a is 1, c is negative 1. So that's going to make that positive all over 2. E to the x is equal to 2y. Right, this is going to... Is it necessarily going to be strictly larger? Yes, right. Because this is going to be parentheses 2y squared plus 4 square rooted. Right, so this has to be larger than 2y. Therefore, it must be added it must be added because otherwise it will be negative. Right, and we can't allow that here. So so this is e to the x is equal to 2 parentheses y plus square root of, we can factor a 4 out, which then gets square rooted to become 2, and then we factor that all the way out, and we're left with y squared plus 1. Okay, all over 2, divide. So e to the x is equal to y plus square root of y squared plus 1. Which means now we want to take the natural log of both sides. This is x equals natural log of y plus square root of y squared plus 1. And x is the no, hang on. X equals, there we go, the inverse sinh of y, which is equal to that natural log. But as long as we just kind of forget that this is here, wink, wink, nudge, nudge, totally works that way. Boy. As long as we totally forget that that x equals is there, we can do a variable reassignation of the inverse sinh and make it, instead of y, just make it a function of x, right? You reassign the variable and make it the natural log of x plus square root x squared plus 1. Okay, now 19. We've got multiple different formulas which are going to be, again, our candidates, which I definitely should have looked at first, but it's fine. Okay, A is going to be log, parentheses, 1 minus square root x squared plus 1. B, log of 1 plus square root x squared plus 1. C, log of x minus square root x squared plus 1. D, log of x plus square root x squared plus 1, which is what we got. E, log of square root of x squared plus 1 minus x. Alright, so that's exactly the opposite of what was in here. Nope, that's not it. Exactly what was in here for C. Right, turns out C would end up getting you a negative number, so it could not possibly be C. So therefore, why not E? Because it's just the flipped around version of that. Eventually, you could make the same argument with A if you did 1 minus the square root of x squared plus 1. If x is a small number, right, we're still adding to 1. So when you take the square root of that, you're still going to get something larger than 1, which you're subtracting from 1. So A will always have a negative on the inside. That's just impossible. C will always have a negative on the inside. That's just impossible. Right? At least A is like, or E, at least E is like somewhat possible if the math were different. Right, so we get negative input to logarithm before both A and C. Just impossible. Throw them out. D is the one that actually works when we actually work this out. So yeah, log of, or natural log of, x plus square root x squared plus 1. All right, 20. The hyperbolic cosine function. So if we go back a bit, right, what we had here was a 2y plus or minus the square root of parentheses 2y, which, yes, it has a negative in there, but it's being squared, so I don't care. That's still going to be 4y squared. And then here we have a minus 4 times negative 1 is plus 4. the inside of this is always going to end up being larger than 2y on the outside here. Similarly, if we work it down a little bit, right, y is always going to be a smaller number than y squared plus 1 square rooted. So having a minus option in the formula means that we will always get a negative input and, a negative value. But the problem is that we have e to the x as our other side. And for all real numbers x, e to the x is always going to be positive. So then here, right, this whole fraction needs to be positive. Yep. All right. Hyperbolic cosine function. Denoted cosh of x is defined as follows. Right, the cosh of x is equal to e to the x plus e to the negative x over 2. So here this is just the switching the sign of our e to the negative x. It's kind of like a conjugate, but not really, of our sinh function. If, that's a bold statement, if the hyperbolic tangent function tanh of x is defined as tanh of x is equal to sinh of x over cosh of x. Find the formula, of course. For the inverse tanh of x. All right, with answers that look like I might need more room. 1/2 log, or ln, of x minus 1 over x plus 1. B log of 1/2 times x minus 1 over 1/2 times x plus 1. The log, okay, let me be consistent. Fine. Log of 1 plus 1/2 x over 1 minus 1/2 x. D 1/2 the log of x plus 1 over x minus 1, or 1/2 the log of 1 plus x over 1 minus x. So again, these two and these two are opposites of each other in each of those pairs, right? So that means that one of them is just going to be the negative version of the other. I don't know really where I was going with that, but seems like we should not get some of them. or there's like a... They have to both be the same sign. So there's going to be a no man's land between two values. Either -1 and +1 for the last two. Or... it's also... No, 2 and -2 for the B and C. Right, because they're going to be opposite signs of as each other when we're between positive and -2 here. And we're going to have opposite signs, so they're going to have a negative interior of these logs between -1 and 1. So that's not possible. Outside of that, though, right, for D and E, from 1, not inclusive, to infinity, and from -1 to -infinity going in the other opposite direction. -infinity to -1, and 1 to infinity. Then we've got a positive quotient because they both have to have the same sign as each other. And then when you divide, they become positive. The quotient becomes positive. So that's interesting. Okay. So if this is going to be the sinh over the cosh, this is, nope. E to the x minus e to the -x over e to the x plus e to the -x. Each one is over 2, but then they just divide out. So this is going to be our tanh. And now we have to do the same thing, essentially. So y is equal to, let's multiply both sides by the No, I don't want the just conjugate. That's going to be... no, I don't want that. Or do I? Okay, if we multiply by the conjugate, then we get e to the x and e to the -2x. So yeah, I'm going to want to multiply top and bottom by e to the x, just like we did for the last one, to make a quadratic. Right, so this is y equals e to the 2x minus 1 and e to the 2x plus 1. We're going to multiply that one to the other side. So we get y parentheses e to the 2x, that's alright, equals e to the 2x minus 1 over here. Trying to get e to the 2x into the same place. So y e to the 2x minus e to the 2x from the other side. And plus y plus 1 equals 0. Right? So this is e to the 2x times, other way around, times y minus 1 plus y plus 1 equals 0. I mean, realistically, right? This is just going to be e to the 2x equals 1. No, don't do that. Let's move it back over to the other side. Negative parentheses y plus 1 over parentheses y minus 1 when we divide through. So this is going to be, if we move that negative down to the bottom and then just commute our y and our 1, we get 1 plus y over 1 minus y. Okay. That is e to the 2x, and yeah, we could probably just pick one right out of the thing right now, but it's fine. Take the natural log of everything. Poor form, don't write it like that, but nonetheless. This is going to get us 2x is equal to natural log, or again, just the log of 1 plus y over 1 minus y. X is going to be equal to 1/2 log 1 plus y over 1 minus y. This is now the tanh of y. Something's trying to get my attention over there. It's ridiculous. So anyway, and again, if we just kind of pretend that this x isn't here, and we say that the function, inverse tanh function of y is equal to all this other stuff over here. This is a function of y, so we can do a variable reassignation. Stop that. Tanh inverse of x is going to be equal to 1/2 log of 1 plus x over 1 minus x. I think that is e. 1/2 log of 1 plus x over 1 minus x. Excellent. It is, in fact, e. I was... I was wrong about that. It's not outside and inside of 1. It's... is it larger or smaller than 1? Okay. So here, if we have x is greater than 1, then we've got a problem, right? Because that's going to create a negative in the denominator. Oh no, yeah, okay. I think I was looking at the... I was looking at it wrong. But if it's a small negative number, The top. Yeah, no, I was right. Oh, man. Okay. It's almost 1 o'clock. Maybe I had to just... We're almost done. We're on number 20. There's 25. 21. Let x be a real number such that sine of x is equal to 1/2, and x must be between open 2 to 3. What is the value of cosine of negative sine of x? Okay, so if the sine of x is 1/2, then that means that the sine of x is going to be the inverse sine of 1/2, which is 30 degrees, or pi over 6. Or okay, so it's either pi over 6 or pi minus pi over 6. Oops. We know it's 5 pi over 6. That's why I wrote a 5. Either of those, or plus 2 pi n, right? So any number of full rotations, we come back to the same points. That is the complete answer for a operation inverse sine. For the function inverse sine, we have to determine the particular domain that we wanted to look at. So the sine of x is going to be equal to one of those things. Pi over 6, pi minus pi over 6 plus 2 pi n. Gonna snooze ad for 5 minutes, see if we can finish this. And maybe, yeah, maybe right out. All right, so we'll do the rest of this. We'll do the rest of the set on Monday, and we should be done with pre-calculus entirely. We'll move on to Calc 1. Again, if anybody has any questions, we'll put this stuff on hold because, you know, anybody else's questions can take priority. If anybody feels like talking about something, you know, come in with a particular question or what have you, and we'll definitely work on it. Yeah, no problem. Okay, so this is x, which then is going to be the inverse sine of either pi over 6 or 5 pi over 6. We'll just do that now, it's fine. Plus 2 pi n. And that x, right? That x must be between 2 and 3. Okay, so if we look at this one, and we say that the sine of x needs to be here. Right, this is the sine of x. And then pi over 6 is like 0.157? No, that's not right. That's pi over... Hell with it. Alright, pi over 6. 0.5235. So that's like... it's almost halfway. Right, 5 pi over 6 is really close here. Yeah, I think this is going to be another one of those. It would be much easier to just graph this. So, flashbang out. Sine of x, and here y equals pi over 6, y equals 5 pi over 6. Oh, right. No, it is not. Okay. Right, that's 2.6, not 5/6. Not 5/6. There we go. Right. 5 pi over 6. So, not going to work. This one, on the other hand, does have solutions. And between 2 and 3, right, this is going to be 2 pi, which is 6. This is going to be at pi, which is 3.14. And so we want a solution that's somewhere between here, and this is pi over 2, which is 1.57. So we want a solution that's somewhere between here and here. What do you know? There's one right there. Right? And there's only one solution. So this is going to say that that x value is that number, whatever that might be. How are you getting real values? That is a good question. Oh, right. Cosine. Cosine of these values. Oh my god. We don't need any of this. What am I doing? Alright, way faster way to do this. The sine of... This was the sine of x was this. We got 1/2. The cosine of the negative sine. Right, and this is always going to be root 3 in here. Note that this has the yep. Oi. Yeah. Oh, wait. Haha, I got more snoozes. Score. Note that, right? This was the cosine of the negative sine, so the sine of x. Yeah, the sine of x was 1/2, so just build a triangle. We want the cosine of the negative sine of x. the negative sine of x is an angle, so it's going down. And then we want the cosine of this, which is based on the horizontal distance. So it's root 3 over 2, the hypotenuse. So we can also double check this by looking at the Desmos value here. You do it on your calculator, right? 2.59052, which if we type in square root 3, right? You can probably see, no. Where are we? What quadrant does this put us in? But right, this is the angle. Jeez. Okay, so we don't want root 3 over 2. We want, what is the sine of root 3 over 2? And then we're making it negative, and then we're taking the cosine of that value. Those values aren't coming out right, so what is it about it? It's going wrong. Is it 2 pi minus that? No. Why say pi minus that? No, because that's just a negative. So yes, I incorporated that into the picture, really, was that it doesn't matter whether we're doing the upper triangle here or the lower triangle here. Our negative sine of x and our positive sine of x are always going to get us the exact same thing. Sorry. The positive and negative sine of x are always going to get us the same cosine value after that. Blorg. Okay. Alternatively, and I think that this is probably a product of seeing what the answers are, or like what they could possibly be. Right, this is going to be negative root 3 over 2. This is going to be root 3 over 2. So this would have trapped me. all the rest of them are big square roots. So yeah, this stuff would have trapped me. Which is, again, the wrong answer, but... but then why, right? Well, okay, so here's the thing, right? The cosine of the negative sine of x is, I think, root 3 over 2, and it should not be a problem. The problem I'm having is that I'm not able to match up and get an x value that agrees to make it root 3 over 2. Okay, let's just revisit this next time, because otherwise I'm going to run into another ad break, and quite frankly, I don't want to do that to y'all. Okay, Dr. Gold just started with actual education, doing office hours. So we're going to head over there and do some more math. I will be back on Friday for gamey type stuff. I got to work on some assets tomorrow and uploading stuff to YouTube. Oh, right, YouTube. I have a command for that. So if you want to check out my gaming or math content, feel free to follow those. VODs will be uploaded there sporadically. What is it, Fridays we've been working on Against the Storm, so we'll probably be playing more of that. And then I want to get into a couple of other games. My brother got me the Swapper, so I better start playing that, otherwise I'll seem ungrateful or something. And I also played a little bit of Nine Souls, and it's absolutely brilliant. So I think I would like to play a cat who knows Tai Chi. Alright, so it's going to be a frustrating, very similar to Hollow Knight sort of thing, but much more colorful. Anyway, see you all later. My name's Obi-Wan Piz. This is N Simplex Pachinko. See you next time. Heading over to see Dr. Gold.